All right, so let's get this going. So I'm actually super surprised that so many people joined this talk. So you are aware how conferences work, right? So usually conferences are built the way that the first talks are not particularly exciting, but as the conference goes, talks get more and more exciting until after the conference, people will definitely return the next year. And so this is the first regular talk after the opening keynote. So do not have too many expectations. Still, first of all, a wonderful good morning and welcome to the most common misconceptions of design patterns, second of N. So quick introduction. Some people might not know me. So I'm Klaus, working as a freelancing C++ trainer, consultant. I've written a book about C++, coincidentally software design. I run a C++ user group together with a couple of other people, the one in Munich, and I do various things at conferences. So and one of the things I do like is indeed software design and design patterns. And so this is the second talk after one that I've given last year, where I was talking about a couple of misconceptions in common design patterns and even the term design patterns itself. This year I want to continue the story, but for this year I actually had to think quite hard what to select because there's so many things to talk about. And this year I decided to talk specifically about a couple of misconceptions that we have about the virtual functions. And so I now talk about two things that I think are pretty important here. And you might know that virtual functions in a community can produce a mixed echo. So some people feel like they're too slow. We have to do something different. And so, for instance, at CPUCon 2022, Ivica Boguslavievic talked about the hidden performance price of virtual functions, trying to tell you they're expensive. But then just in the year after, somebody said, wow, optimizing away virtual functions may be pointless entirely. And so there is this battle. Is it good? Is it bad? And I'm not happy to chime in. But from a different perspective, I want to take a look at this from the design perspective. And so today we're going to talk about two topics only. We're going to talk about CRTP, one of the beloved cryptic abbreviations that you have in language. And we are going to talk about stud variant specifically. Good. So let's start to talk a little bit about CRTP, which is, from my point of view, one of the things that I definitely should talk about. So you might not know CRTP. It's actually something pretty old. It's from 1995, and it's named after a paper that James Coplin wrote in 1995 after observing that a certain template-based pattern appeared in a couple of code bases. And so, just in case, indeed, you have not heard about this, very quick intro. So we have a regular inheritance hierarchy. I chose one of the classic ones. So we have animals. I have a sheep-derived class. Now this inheritance hierarchy, first of all, has a templated base class. And now, right away, the special detail about this technique, the derived class inherits from this base class, but passes itself as a template parameter. Which is curious indeed. Does this even work? Absolutely, because as soon as you say class sheep, you kind of have forward declared this. And yes, you are allowed to instantiate a template with an incomplete type. So perfectly fine, perfectly valid. But now, so you now see what the T in the derived in a base class is. So this is the derived type. And so one of the things that we now do in order to communicate this pattern is to name the template parameter derived. Now this is a typical name for that. So then it's a base class, but it's not really used in any virtual way. And that's pretty much the point. We want to get rid of virtual functions entirely. So we tend to make the constructor, the default constructor, and even more specifically the destructor private, which kind of means that we cannot access them anymore, but the derived class has to. And so we befriend the derived class, which actually is even a protection that we not accidentally use a different wrong type here. So this is a pretty solid protection against any kind of misuse. In a derived class, you don't have to meddle with the destructor at all. Yeah, remember the rule of 5. Leave it. Yeah, this is just to mention there's nothing special. Now, of course, a base class is about defining an interface, a contract, something that people can use. And so this is the same thing again. So animals make some sound. But more specifically, it's not a virtual function. But still, the real implementation must be in the derived class, because only the derived class knows exactly what needs to be done. So if it's not a virtual function, how do I get from here to there? Well, we know what we are. We are a derived. And so we statically convert ourselves to a derived type with a static cast, which is perfectly valid if we are truly a derived. And on the derived object, we call the makeSound function. So, and in this entire scheme, usually it's used by just writing functions that take an animal of derived. And so now in this function, I can use all kinds of animals, all the derived types. I can call makeSound whenever I want, and there's no virtual function call at all. No virtual dispatch, although I have a proper inheritance hierarchy. So now if indeed some people have seen this for the first time, oh, wow, I know the reaction. Wow, that's amazing. That's the holy grail of inheritance. Oh my God, why haven't I done this? And of course, you have great plans for next week. Yeah, this week is the conference, but next week, you're rewriting the entire code base with CRTP, making it fast. But before you actually do that, and before you set any big plans, no. There's some limitations. Two, at least, they're pretty serious, and so I should now mention them quite quickly. So first, something that you might not have realized initially, if you use the CRTP pattern, every derived class has a different base class. Now, this actually has quite severe implications, so I say it again. Every derived class has a different base class. So there is no common base class anymore. You cannot have this vector of animals, which is what people usually want to have if they use some kind of inheritance. Now, this is really different. But there's something else that people are bugged with quite quickly. I've shown this print function before, and yes, this print function is a function template. And it kind of has to be, because this is the only way to really mention, without explicitly naming it, the derived class. Now, this is the print function for some specific animal. But this kind of means that pretty much everything that comes into contact with this animal base class is itself a template. And so interestingly, the CRTP is a little bit like a virus. Everything that comes into touch with these base classes becomes itself a template. Stuff is moved from the source file to the header file. Good source code is suddenly turned into template-only, header-only libraries. Whoa! Your compile times might be super miserable afterwards. And many people have reverted all of these changes because, well, even compile times is an important property. So, okay, now, hopefully most people have dropped the idea to rework everything in CRTP. That's what we have today, because actually we have something new. And the new cut on the block, which is kind of introduced by Ben Dean in 2021, commonly called as deducing this. So what he's talking about is a new feature in C++23, the feature that we refer to as explicit object parameters. So when I take the example from his talk, make it a little bigger and a little more specific so that you get to see what's going on. So again, this is an example for CRTP. You now recognize this with this derived name up here. The base class provides a scale function, which, however, eventually calls some get value and set value on the underlying type, the derived type. These two functions will be provided by derived type. Okay. Now, in the main function, I create a sensitivity object, some initialization, and then I call scale. Well, I call the function on the base type. But the base type knows fully well what it is, so it can call the derived classes get value and set value functions. Good, so this works nicely. But admittedly, it's a little technically complex. It's not something that is super simple to understand. And so now, here's the new idea. In the base class, we introduce one of these explicit object parameters, this pointer. So now, since C++23, you are allowed to explicitly express the type of this object. You write this, then the type of that, and you've commonly now used the name self as a parameter name. So now you can call self-setValue and self.getValue to call these two functions. So they're not template parameters anymore. It's simpler. And you have full power to express what the type of this object is, whether this is const or not. You can use forwarding references, you can use whatever you want to. Pretty simple. Whoa, that's amazing. This is nice. And people were quite intrigued by that. And Ben, kind of in one sentence, said, so CRTP really just, I guess, goes away. Oh, this motivated people to show off in their code. Indeed. Now, in the last year, 1.5 years, I've seen many talks that kind of picked up the idea and just showed how beautiful the new era will be with explicit object parameters. First example, second example, then have been a couple more examples that I unfortunately did not find online anymore. So now, let's take a look at the examples that they presented in their talk, at least the gist of it. I'm using my animal and sheep again. So my animal has this makeSound function, which calls makeSoundImpl in the derived class. So in the base class, I now use this explicit object parameter. I make it a reference to const, doesn't have to be a forwarding reference all the time, so this is nice. Now in the main function, I create a sheep, but I also store the sheep as a pointer of animal, a reference to animal. I can do that. There is an inheritance hierarchy. And then I call sheep.makeSound and animal.makeSound. It's simpler, isn't it? It's amazing. It's so beautiful, but it doesn't compile. It doesn't work. And indeed, surprisingly, this happened in a lot of talks. They presented code that would just not work, not compile. That is surprising. Why is that? Well, I think there is a big miscommunication, and that has to do with the term CRTP. Now, in the talk of Ben Dean himself, he actually explains why this is not possible to work. So it's actually this line. If you have a base type, base object, and if you try to call the if you call a base function on this base type, it will never derive the derived type. So this explicit object parameter cannot deduce the dynamic type of an object, but it can only deduce the static type. So as soon as you call something via the base thing, it will always be a reference to the base. Actually, this is the line. So no, this can actually not work. Technically, this is limited. But why the confusion? Well, on the slide that I've shown before, there actually is a nice link to fluentcpp.com from a blog entry from 2017. So this was a pretty good blog about what the curiously recurring template pattern can bring to your code. But that's an interesting block of comments that's now interesting for us. But there are several ways the CRTP can be useful. Here I'm presenting the one that I see most in code, adding functionality, and another one that is interesting, but I don't encounter as often, creating static interfaces. All right, adding functionality, static interfaces. That's the difference. Well, adding functionality is what I've shown in the numerical functions and sensitivity example. The base class provides some function that the derived class is supposed to use. However, the use is quite important. I never really use the base class specifically. So it's just some kind of provided functionality. So I create a derived object and I call scale via the derived object. This is where CRTP indeed can be very, very nicely be replaced by explicit object parameters. Here again. This works. This is fine. I will always use the derived object directly. However, we've also seen the other example, the animal example, animal sheep. Same slide as before. In this context, at this point, the static cast to derived is an explicit going to the dynamic type of the thing. So I know the dynamic type because I statically have found it to my base class. However, if I replace this with an explicit object parameter, and here, this again, then unfortunately the last line just cannot compile because I cannot deduce self to be the derived type. And so that does not work. However, in this context, I truly use this thing via the base type. And so I hope you see the difference between the two. One is about adding functionality, one is about creating an interface, a static interface. And that pretty much is these two names. So there are two forms of CRTP, but the term, because of this, is kind of ambiguous. So if I say CRTP to you, you might think about exactly the opposite thing. That is kind of a problem. Now, this is an ambiguity, a misunderstanding. This led to people using the wrong thing in their talks. So what we do need is new terms. We need new terms in order to disambiguate between these two things. So, and I believe we kind of have them already. But before that, and I publicly apologize, I missed the opportunity to do something. In my book, I actually talked about CRTP and I showed the two different things. I did not provide new terms though. Although it's a book about terms pretty much, about terminology, that's a chance I totally missed. I'm totally sorry. But today I'm gonna change that. So, CRTP for static interfaces. That's the animal sheep example. So in this example, I provide a base class for a related set family of types. That's the point. I want to have a common interface for everything. And I'm going to use it via the interface, via the base class. It's an inheritance relationship. And so in this case, I really introduce an abstraction. And so I would say this is pretty much a design pattern, something where I can create a static interface. And this is, I believe, the name that we should use for this technique. I think static interface is good, which, by the way, is exactly the term that Jonathan Bukhari used in 27 also. I believe this is a good term. So let's use this from now on for this particular technique. The other technique, though, adding functionality via CRTP, well, it is different. So in this case, the base class provides some implementation detail for the derived class. It's just introduced into the class. So I don't really create a common interface. It's not really about a base class, some use via the base class. And so this does not introduce an abstraction. It's more like an implementation detail. This is what I would call a mix-in. And not just me. This is the common term for this kind of technique. So we mix in some piece of functionality via some base class into a derived class. And it's never about the base class. It's about the derived class having this piece of functionality. So I believe this is the two terms that we should be using consistently. And then the confusion totally goes away, because if you say static interface, then well, it should be clear. So prefer to use the term static interface to express the intent to create a family of types, a static family of types. And static interface is a design pattern. It's something that you consciously to create this connection. Unfortunately, because it's a design pattern, explicit object parameters, pretty much an implementation detail, simply cannot replace CRTP. And prefer to use the term mixin to express the intent to inherit implementation details from a base class. Now, so it's not about the base, it's about adding this functionality to another class. This mixin, that is an implementation detail. And that can very well be replaced by explicit object parameters. They are a pretty elegant, pretty good alternative to the good old CRTP. All right. But now, of course, some of you say, wait a second, Klaus, I'm not entirely convinced about what you're saying here. No. CRTP has always been a little special, technically contrived, etc. Isn't it just much easier to replace CRTP entirely? Also for these static concepts with a C+20 concept? Isn't this just what we should do today? Oh, that's an interesting thought. So let's take a look. So I've now recreated this animal sheep example, but now really differently. The sheep class itself is now a standalone class. There's no base class anymore. There's also no template parameters. Sheep just has make sound function. The base class now has been replaced by a concept. A concept that just clearly expresses that every animal has make sound function, member function indeed. And if I now write a print function, which actually is can be before the sheep because it's independent. If I write a print function that takes some animal expressed explicitly with the with this concept, then I can call make sound and know that this is going to work because I can only pass things that do have make sound like the sheep. That's it, right? This is pretty much the same thing. No, it's not. So what can I pass to print? Can pass to sheep. Pass anything. I can pass this guy here. I can be printed too. I can also pass this guy. Me too. And this one. It is logical to assume that I can be printed too. Anything can be printed. And you know how we call this? Duck typing. Okay, now you get the reference. This is what we call duck typing. Anything can be printed as long as it has a make sound function. That's definitely not the same thing. Really not, because accidentally I could now print something that has nothing to do with my idea of printing. So, I admit, yes, the concept idea is a nice one, but we have to do something else. We have to introduce something that really creates a family of types, an explicit family that really knows it belongs together, like a tag class. So I introduce some empty animal tag. And additionally, I say that animals must have a make sound function, but they also must be derived from animal tag. That's now a precondition for animals. Print is unchanged. It now accepts animals. But now the sheep class is required to explicitly derive from animal tag in order to be an animal in my context. And that's exactly what static interfaces are about. It's about creating this family of types, a specific group of types that opts into being an animal. And now this poor guy cannot be printed anymore. Me neither. And it's logical to assume that I'm unprintable now as well. So suddenly it's not duck typing anymore, suddenly it's specific. This is exactly what static interfaces are about. This is what we've used CRTP for. And so, okay, I give you that. Also, CRTP for this application has an alternative, perhaps a more modern one. But note, it still has to be a base class. It has to be something that cannot accidentally happen. It has to be something that explicitly happens, this explicit opt-in. So it has to be a base class and cannot be some member type, whatever. This could happen accidentally. All right, so still prefer to use the term static interface to express this creation of a static family of types. And okay, perhaps there's an alternative CRTP, but still, I would say this is not totally out of the game. CRTP might still be interesting. And same as before, mixins, oh yeah, this is definitely something that today I would implement by means of explicit object parameters. It's just simpler, more beautiful. Good, all right. So much for CRTP. Let's talk a little bit about the other thing, variant. Variant. So let's start with a toy example. And okay, some people know me. Some people know that I have a go-to classic example. And I know it's still boring, but I'm still gonna use it today. We're gonna draw a couple of shapes again. Yeah. I don't think it's funny anymore, but I didn't find a better example. I'm sorry, I apologize. However, today I'm actually setting a couple of requirements. I want to be able to introduce new kinds of shapes like ellipses, rectangles, perhaps a couple of triangles too. I want to be able to add new triangles later. So it should be extendable with new kinds of shapes. Good. I expect that this happens in a big code base. So we're talking about 10 million plus lines of code, not just 200 lines as usual slideware examples. And I think this is also a project that is developed by 100 plus developers. So we're thinking big, we're thinking large scale. All right, and how could we draw shapes? Well, of course, we could start with an inheritance hierarchy, a shape base class. Virtual destructor, of course, but also, for our case now, the most important function, a virtual draw function. There's several other virtual functions as well, but draw is the important one. Then circles, as one example, would inherit from shape. But now here's the issue. The circle now would have to implement draw, simply because this is the bidding of the base class. But Circle doesn't want to. Really, Circle doesn't want to know about graphics libraries, about how to draw itself. This is where I've thrown a design pattern, the strategy design pattern. So we're going to introduce a base class called draw strategy. That thing is going to represent the implementation details of drawing. That thing is able to draw a concrete shape. Could be circle, could be square, something else. Now, this is exactly what the circle uses. So it expects a draw strategy in its constructor. It stores this draw strategy as a member. Whenever somebody calls draw, this draw strategy, this drawer, is used to draw the circle. Nice. So it's testable, it's flexible, it has a lot of very positive qualities. Okay, just to have another one, because else circle would feel so lonely. There's a square too. There are other shapes as well, but it's pretty much the same thing. Now, I have this base class, the shape base class. So I can now actually store a lot of shapes in a vector of shapes, a vector of unique pointers of shape. That's what are called shapes. It's shorter, it's quite convenient. Okay, but there's more. I need to create these shapes too. How do we do this? Well, I would like to abstract this too. So I introduce a shapes factory. Oh, that's a favorite term of many people. I know, but still stay here. It's not as bad as it looks like. So we'll have a shape factory that creates shapes, meaning a vector of shapes, based on some file, some content that we parse, and then read all the shapes from that. Good, and then we can draw all the shapes. Some function that just runs over all the given shapes in a vector and calls draw. Good, and last but not least, because we can create them, we can draw them, why not have a create and draw shapes function that takes a strategy, some input file name, and it first creates the shapes and then draws them all. Nice. All right, now that all of this is in place, we can actually start to do some real work. So we could, for instance, do the drawing by means of OpenGL. This is what my OpenGL drawer does. OpenGL drawer has a couple of base classes because it implements the draw strategy for circle and for square, potentially a few more. And so it implements a couple of draw functions by means of OpenGL, of course. So it stores colors, textures, transparencies, whatever is required. And then, of course, I can introduce some shapes factory. That's a lot of code. You do not have to read this. The one important thing is that we now read something from file, for instance, detect that circle is specified and we read a circle from file. Perhaps it's a square, then we read a square from file. We package everything into this vector of shapes and in the end return that thing. Good, nice. All right, and with all of this, we're done. We can create a factory and we can call create and draw shapes to just read everything from this file and draw this stuff. Great, isn't it? Beautiful. It works. However, let's think a little bit about our design again. There's one very important aspect that I'm now focusing on, and it happens right here. Right here. There's a line, implicit at first, but now visualized. There's an architectural boundary. And this is a pretty important point here. Because, well, you and me, we want to work together. You want to do some stuff, I want to do some stuff. Okay, I know that high level and low level is always a little confusing. Stable vault. Okay, let's make it simple for today. This is my code. This is your code. Okay? So in my code, I just want to get a couple of shapes. I want to draw them, but I don't care which shapes. I really, really don't care a lot. But I have everything in place that this now works a lot. It works very well. So you can now, if you want to, introduce a rectangle. Your geometry of choice. Yeah, you do something. Again, not important to look this through, but again, there's of course a draw function that you configure by means of some draw strategy. All right. You can also, if you want to, introduce the according OpenGL functionality. It's on your side of the code. You selected OpenGL, and I don't really care about this. So you just implement the new draw function for the rectangle. And you, again, you can introduce the according code to read rectangles from files also. Nice. There's no change in here. Yeah, we can still do the same thing in the main function. It works, right? It works. It just works. You can do what you want. I can do what I want. We're both happy people. Okay. Now, you look a little unhappy at this point. This may be because it's early in the morning, but this can also be because perhaps you do not like this style of programming anymore. And okay, perhaps I've just the talk to kind of represent what I mean. Or not the talk, first the book. So this style of programming. This is, you know the book probably, you've seen it at least, perhaps some people have even looked into the book. This is what we refer to as the Gang of Four book. Gang of Four because of the four authors. And it's a classic. This year it actually turns 30. 30 years ago, these four people collected design patterns. Classic object-oriented solutions to common problems. And so the style that you just saw is pretty much from this book, the GOF style. Yeah, the GOF style where inheritance and virtual functions pretty much are the answer to all the problems. Okay, almost. 21 of the 23 patterns are based on inheritance. But, exactly, you may remember this talk. Perhaps you've heard about it at least. Inheritance is the base class of evil. Even after all those years, I kind of like the title. It's funny. It's a clever choice of words. However, apparently, this talk tells us, do not use inheritance. It's bad. It's evil. Now, it's right here in the talk. So based on that, of course, people kind of got the message. So, talk from 2022, using modern C++ to eliminate virtual functions. Ooh, sounds kind of aggressive. Eliminate virtual functions, but I think that's kind of the spirit. And a little bit what I said in the beginning too. We don't like virtual functions anymore. They're too slow. That's not the style of programming you use anymore. Also, might have been last year or the year before. I think it was the year before. To one of my submissions to some conference, I got this review from, so this feedback from a reviewer for one of our talks. I believe that object-oriented programming, and especially its theory, are overestimated. C++ has always had templates, and now also has std variant, which makes the use of inheritance unnecessary. Oh, std variant. So if you've not used std variant before, beautiful. And of course, that's the solution to all the problems, right? Std variant. The solution to replace inheritance hierarchies. So let's use this. Let's modernize our code with a std variant. So I start with a circle class. Note, there's no base class anymore. Yeah, no base class at all. There's also no virtual function. Pretty much circle is at the top of the entire file, meaning there's also no draw functionality. It's totally decoupled from this. This is good. Square the same. Squares, rectangles, triangles, it's pretty much the same thing. So no inheritance, no dependency on graphics code, no base pointer anywhere. Nice. I also will not, you will see this more later. There's no manual lifetime management anymore. And it's just so much less code to write. So much simpler. Good. Then the shape type has been replaced by a variant. Variant of circle, square, or potentially also a couple of other shapes. So this now is pretty much my abstraction of shapes, hence the name. The variant now represents a shape. And I directly store a couple of variants in the vector. No more unique pointer, no more pointer at all. Simpler. It's just simpler. Good. Now the shapes factory. Okay, it's not much shorter, but perhaps a little simpler because I do not have to make unique circles and squares anymore. I just create objects, values, put them in the vector. I think this is definitely an improvement. Okay, and also no inheritance necessary. There's no shape factory base class anywhere. It's just the factory itself. Okay, this is what I said. Now, of course, there's another opportunity to use a variant. Let's use it. So we have a factory, which at this point is just a variant of the shapes factory, but there could be more. Oh, great. All right, then the OpenGL drawer. That pretty much is the same as before, but again, no base class. Good. And perhaps a little simplified because a couple of other things might also not be necessary. Okay, I think it's in total simpler. But there's another opportunity variant. So we can now have all the drawers, the different drawer implementations in a variant. At this point, maybe just one. Okay. So, and here, one of the most interesting lines that I have. Draw all shapes. Now traverses all the shapes in the given vector. But it also, at the same time, uses this visit. Of course, I'm visiting the variant. But now I have two things. I have the shape, I have a drawer. Well, I'm just using multi-dispatch with the visit function. I pass two things, the drawer and the shape, two variants, and the two things are just combined. Oh, this is amazing. Multi-dispatch in C++, by just a single, very simple line of code. Ooh. Create in shapes. Pretty much the same. But okay, the visit is now used as well. And then in the main function, I would simply create a factory, some drawer, and I'd put them together in the create and draw shapes call. Good. And I think you kind of agree. So much better. There's no inheritance. That's a pretty functional approach. Very clean, I would say simpler. There's no smart pointers, not raw pointers. We have values. Then there's no management of graphics code. This is just extracted. No dependence in that. This is fantastic. Lifetime management is also much simplified. It's less code to write. It's so much simpler. And on top of that, it even has better performance. Oh, now, of course, now people are staring at me. Performance. Now, Klaus, I want proof. Okay, I get that, but performance. This is usually the toughest part of any talk. Yeah, if somebody presents performance results, in the end, it's always bickering about little differences. Oh, on my compiler it's different. Oh, on my machine I have something else. Okay, now I'm going to actually show you a couple of performance results. I do, but only under one condition. So you promise that you will not complain about my performance results. Can you do that? Okay, so I take this as a yes. Good. So they are really not, do not take them too serious. This is just qualitative results on my machine, but still I should show what I'm doing. So I have 6 different kinds of shapes: circles, squares, ellipses, rectangles, hexagons, and pentagons. And please do not expect that I took the time to really implement a full-fledged flexible hexagon. It's an equal-sided hexagon and also pentagon. I'm using 10,000 randomly generated shapes. I perform 25,000 translate operations, each one of them, which means it's a super simple, cheap operation. But this actually reveals the real performance difference in the intrinsic setup itself. And I'm benchmarking with, I would say, recent compilers, GCC 13.2 and Clang 18.1.4. Okay, and last but not least, my machine that I used was an 8-core Intel Core i7 with decent numbers. Good. So the performance. On my machine, this classic object-oriented solution that you just saw runs in this time. And now, again, please don't make it a race between GCC and Clang. Totally irrelevant. If I use std variant, okay, GCC, much better. Clang, not so much, but there's another very popular variant implementation on GitHub, mpark variant. If you use this one, both compilers agree, much faster. Faster. And again, if you see these numbers twice as fast, you're making plans for the next week. I'm going to replace all my inheritance hierarchies with variant. Okay, I can already kind of give you the gist of this talk. Please don't, yeah, please do not make plans for that too. Because let's take a look. It looks like this is just fantastic. It's fast, it's simple, it's beautiful. It really is, no doubt here. Let's talk about design again. So again, I'm trying to find the point where we can separate concerns, yeah, where your code ends and my code starts, or vice versa. So keep it simple for now. Let's do it right here. So I think these two functions, draw shapes and create and draw shapes, that's my functions. I think so. This is my two functions. I want to draw all the shapes, not knowing what they are, and I want to create and draw them. Okay, this is your code. Okay, of course, it's kind of incomplete. I don't want to know about the OpenGL drawer. I'm not interested in OpenGL at all. You may be, I'm not. And so the OpenGL drawer, that's your code. So that goes into your code, of course. Okay, that's yours. Okay. There's one little wrinkle. Drawer. That type is actually used in my type, in my function. Okay. Perhaps I was a little too quick. That, of course, kind of still belongs to me. Okay. But oh no. OpenGL drawer. I don't want to know about the OpenGL drawer. That's not my stuff. But now it's still my thing. So it doesn't work. It really doesn't work. To be honest, from an architectural point of view, with our set goals, this actually is an architectural disaster, a total failure. It doesn't give us what we actually want to have. Standard variant doesn't hide any type. It very much declares all its types up front. It's in the type, variant of, blah, blah, blah. These types are visible everywhere. I have a dependency on these types. I cannot simply extend them. So, standard variants is definitely not a silver bullet. And most definitely, it's not a replacement for virtual functions. Cannot be. Never has been, will not be. On the contrary, standard variant is pretty much the architectural antipode of virtual functions. The opposite. How? Well, let's quickly compare variant versus virtual functions. So first of all, because also here I think there's kind of confusion, standard variant still is dynamic polymorphism just as virtual functions are. At runtime, at dispatch, at runtime I know what to do. This I would say is a little functional programming. This is object-oriented programming. But this makes the difference actually. Because in a variant context, you work with a fixed set of types. It's in the variant type itself. This is the fixed set of types you work with. This is not supposed to be extendable. But in an object-oriented setting, the idea is to enable an open set of types. But then with functions, it's just the other way around. With a variant, you can very easily, very conveniently introduce new operations on this fixed set of types. You have an open set of operations. But with the virtual functions, you have a closed set of operations. You cannot just add a new virtual function into a base class and nothing else will have to be done. Now, that is a difficult thing to do. And so, you see, it's pretty much the opposite. So you cannot simply replace them. And that is pretty much because, after all, this is a pattern, a design pattern. We call this the visitor design pattern. That's what basically hides behind this idea. And so, what I think many people fail to realize is that standard variant is indeed not a replacement for virtual functions. It really shouldn't be used as such. It's something different, a specific solution for a specific problem. Good. So, I've seen perhaps a common pattern between these two patterns. Now, they're not directly and they're not good replacements of virtual functions. No, they're not. So neither CRTP nor state variant are replacements for virtual functions. Generally, always think about design patterns as some dependency structure. This is what they are. Every pattern with every name introduces a different dependency structure. What depends on what? What needs something else? Because of that, design patterns have some architectural properties. So it matters which pattern you choose. You want a certain design and architecture. So you cannot just replace one design pattern with another one, believing that this will not make any difference. And I think this is what currently is forgotten. This is why we talk about let's get rid of virtual functions. This design aspect seems to be overlooked too much. So please, final guideline. Think about your design architecture first. What do I want to do? What do I want to extend? How do I want to move forward in the future? And after that, you think how to implement that. And so if you decide that you need a lot of new types later, that you want others to write new types, a variant is just not a solution. And so consider only the patterns/abstractions that fit your design. I think that's the right thing to do. First the design, then the implementation. And please do not design based on performance requirements. I mean, sure, performance is important, but I think maintainability in the future might be much more important, at least for most of us. And so, architecture and design first. Okay, thank you very much. All right, so we have a lot of time left. Some time. Are there any questions? Okay, and remember, you promised not to complain about my performance results, so these questions are out. But if not, thank you very much and enjoy the rest of the conference.